Hello students, this is Aditya Chakraborty, lecturer in Electrical Engineering Department of Sri Ramakrishna Institute of Science and Technology. Today I am going to discuss about the different types of speed control method of DC motor. Now the first slide is the speed equation of DC motor. So to derive the speed equation of DC motor, we start with the equation for DC motor's EMF equation, or that is the electromagnetic force equation, or you can say the DC generator EMF equation. Both are same. We know that the EMF equation of DC motor is equal to E equals to NP phi Z by 60A. So that is the back EMF equation, or the EG, that means the generated voltage equation of the DC generator. So hence, rearranging the equation, N equals to 60A E by PZ phi. So if we assume the PZ by 60A is a constant K, then N equals to E by K into phi. Hence with E equals to V minus I array. So that means E stands for the back EMF, which is equals to V, that is the supplied voltage or applied voltage, minus IA into RA, or product of IA, that is the armature current, and RA is the armature resistance. So now we derive the speed equation of DC motor, N equals to V minus I array by K into phi. So that is the speed equation. That means the speed is directly proportional to the supply voltage or applied voltage, and inversely proportional to the magnetic flux or the field current of the DC motor. Now the speed control methods. So there are several numbers of speed control methods. The supply of the motor is directly proportional to the supply voltage. Number 2, the speed of the motor is inversely proportional to the armature voltage drop. And speed of the motor is inversely proportional to the flux due to the field. Thus, the speed of a DC motor can be controlled in 3 ways. By varying the supply voltage, by varying the flux, and by varying the current through the field winding. And by varying the armature voltage, and by varying the armature resistance also. Now, the next slide is comprised with the armature resistance control. Here you can see the circuit diagram of armature resistance control method. Here we are assuming 2 numbers of DC motor. One is series DC motor, another is shunt DC motor, and a resistance or a variable resistance is connected with the armature of the motor, and by varying this armature resistance we can control the speed of the DC motor. So now the statement of the armature resistance control. So figure 1, that is the first figure, speed control of DC shunt motor by armature resistance control. And in the previous slide we can see the figure B, what is the speed control of DC series motor by armature resistance control. So in this circuit, a variable resistance, that is RE, is put in the armature circuit, and the figure A above shows the process of connection for a shunt motor. In this case, the field is directly connected across the supply, and therefore the flux phi is not affected by variation of RE. So you can see that in the previous slide. So here it is the shunt motor, and you can see this is the armature and this is the armature resistance, and this is the variable resistance which is connected with the armature. So if the current through the armature can be controlled by the resistance, then the speed is also be controlled. And this current is independent, so the field flux current cannot be changed. And now we can see, so this is the armature resistance control of shunt motor. Now the next slide is the field flux control. Here you can see the field flux control method. So same as the armature control method, there are two numbers of motor, that is the shunt motor and this is a series motor. And here you can see there is a resistance or variable resistance, that is RC, is connected in series with the shunt field winding, and here is another resistance, that is RD, which is connected with the series field in parallel, that is also a variable resistance. So if we control the resistance or variable resistance, we can control the flow of current to the shunt field winding, and as well as if we control or if we increase the resistance of the parallel resistance of this RD, then the more number of current will flow through the series field winding. And if we reduce the value of the resistance of the RD, then the maximum number of current will flow through the RD resistance, and the minimum number of current will flow through this RSC or through this series field winding. So that means, and the two current, that is the series field winding current and this RD resistance current, are meeting at that very node. So the total number of current which is supplied to the armature of the DC motor cannot be changed. So that is the field flux control method of series motor. So according to the speed equation, we know that if the field current is increased, then the speed of the motor can be reduced, and vice versa. So that is the field flux control method. Now the field flux control, figure 1 or figure A, the speed control of DC shunt motor by variation of field flux, and the figure B, the diverter, that is called field diverter, which is connected in parallel with the series field resistance or series field winding. The diverter is in parallel with the series of DC motor. Since the field winding produce the flux, and if we control the field current, then the speed can be controlled. In the shunt motor, speed can be controlled by connecting a variable resistance RC in series with the shunt field winding. So in the previous slide we can see the diagram. So RC is called the shunt field regulator. A variable resistance RD is connected in parallel with the series field winding. The resistor connected in parallel is called the diverter. A portion of main current is diverted through the RD. Okay. Actually, practically, the shunt motor is a constant speed motor, because we can't control the shunt field current in a wide limit or wide range, because the shunt field current is has a very small value, because the shunt field resistance has a very big value. So the shunt field current has a minimum value. So we can't control the current in a wide range, or we can't control the speed of the shunt motor by the field control method in a wide range. So now the next slide is the armature voltage control, or you can see the WARD-LEONARD method. So what is WARD-LEONARD method? In 1871, two scientists, Ward and Leonard, adopt this method, and this is known as the WARD-LEONARD method of speed control. Here you can see three numbers of machines are connected. One is a AC motor, it is an induction motor, three-phase AC motor. One, a separately excited DC generator. Another is a separately excited or double excited DC motor, and it is connected with mechanical load. So we have to control the speed of the DC motor by using this whole mechanism. So how can it be possible? This AC motor or this three-phase AC motor or induction motor is act as a prime mover of the DC generator. So it supplies the torque to the armature of the DC generator, and by varying the field flux, this is a separately excited DC generator, so by varying the field flux we can increase or reduce the induced EMF of the DC generator. So the speed of the DC generator is constant because the speed of the induction motor is also constant. So if we increase the field current of the DC generator or field excitation of the DC generator, then the then the induced EMF in the armature of the DC generator is increased, and it is fed to the motor terminal or DC motor terminal, and which is also separately excited DC motor. And so when the voltage or rated voltage is supplied to the DC motor terminal, then the DC motor will tends to rotate. But if we want to increase the speed of the DC motor above its rated speed, by supplying of the rated voltage, the DC motor speed can be at maximum rated speed. But if we want to rotate the DC motor in above the rated speed, so what we have to do? We can't increase the voltage because the supply voltage is constant, which is supplied from the DC generator. So we have to reduce the field current of the DC motor, and if we reduce the field current of the DC motor, then the speed also increased, because we know that speed is inversely proportional to the field current or field flux. So by this method of speed control, wide range of speed control can be possible. So this is known as WARD-LEONARD method. Now that is the statement of WARD-LEONARD method. We can control the speed of the DC motor by varying the applied voltage to the armature. WARD-LEONARD system of speed control works on the principle of armature voltage control. In this system, M is the main DC motor whose speed is to be controlled, and G is a separately excited DC generator. The generator G is driven by a three-phase driving motor, which may be an induction motor or an asynchronous motor. The combination of AC driving motor and the DC generator is called the motor generator set. So that is the WARD-LEONARD method. Now the next slide is some advantages of WARD-LEONARD method. So these are: it is a very smooth speed control system over a wide range from 0 to normal and above normal speed. Okay, so that is a wide range of speed control can be achieved by this system. The speed can be controlled in both the direction of rotation of the motor easily. Motor can run with a uniform acceleration, so we can accelerate the motor with a uniform acceleration by this method, because a smooth speed control can be achieved by the WARD-LEONARD system, and speed regulation of DC motor in this WARD-LEONARD system is very good. That means speed regulation means no load speed to full load speed. Okay, so difference between the no load speed to full load speed is very low, because in case of sudden load change, there is no such vibration in the motor, or there is no such enormous speed change in the motor occurred. And now the drawbacks of WARD-LEONARD method. The system is very costly because two extra machines, one induction motor and another generators are required for this system. Number two, efficiency of the system is not sufficient, especially if it is a lightly loaded. Number three, the larger size and weight requires more floor area and frequent maintenance is needed due to uses of so many machines, and due to a huge vibration caused by the windage loss, there is a noise is produced in the drive. So that's all about the speed control of DC motor. Thank you.